continuing with our idea about collision theory, and we're going to work with reaction pathways. Remember that yesterday we said that reactions will only take place if two things happen. And those two things are that they have enough energy and they have the proper orientation to cause those reactants to recombine into products. So we've got a couple terms that we're going to want to think about when we look at reaction pathways. And I'm going to make a little drawing here. On your notes, I wouldn't worry about doing this because we've got some places later on where we're going to label this. But the first thing is the activated complex. So I'm going to do a quick sketch of just some sort of potential energy diagram where this is our energy on the y-axis and this is just time on our x-axis. So the first thing I want us to think about is the activated complex. And that is usually abbreviated with AC. And our definition for activated complex is that it's just a high energy, short-lived transition phase. And it's where your reactants start to break up. So reactants break apart and products form. All right, so looking at my quick little sketch there, do you see a spot where you have really high energy? Yes, ma'am, I like that. Okay, so it's right up here, right at the tippy top. That would be our activated complex up there. Okay, then we can also talk about our activation energy, and it is labeled like that. You've got an E with a subscript A for activation energy. And that's the minimum amount of energy that you have to give your reactants to be able to have them turn into products. So let's say minimum amount of energy needed for reaction to take place. Okay, minimum amount of energy needed for the reaction to take place. So let's say that we're down here at the bottom of this hill. In fact, this is the very beginning. This happens to be the energy of the reactants. If I'm down here at the bottom of the hill and I want to get a bowling ball to roll up and over the top of the hill, then I need to be able to give that bowling ball a minimum of that much energy. So that's what we see as our activation energy. And let's go ahead and we will label that on the diagrams that we have on our notes. But before we do that, let's just make a note here also that if you have a high activation energy, that means it's going to be a pretty slow reaction because it's going to take a lot more energy in order to get that bowling ball up and over the hill. So high activation energy means slow reaction. So now we go to the diagrams that you guys have on your notes. And this first one. The first one says label the location of the activated complex on the graph. So we just did that already, but hopefully you guys can see where it would be on this one. And you see right up here at the very tippy top, that is my activated complex. All right, let's think about how we can do these. We'll start with A. This right here, the energy that's required right here, what are you always starting with in a reaction? What do you start with? Reactants. That's it. So this is, I'll just write E of reactants. The energy of your reactants. That's right here. Which means the energy of your products would be which one? How would you label that? D. So this point right here is your products. D is energy of products. Okay, let's say, what if we wanted to look at the activation energy of the forward reaction? Activation energy, how would you label that? Good, so you've got the addition there. You've got a It's of the forward reaction, you're starting here and you want to get up here, so you've got to give it this much energy, which is your B plus C, activation energy. I am going to make a note, though, that that's the activation of the forward reaction, because which one would be the activation energy of the reverse? And sorry, I'm too close to the board. It's going to be B in this case. Activation energy of reverse reaction. So if you're standing right here, you need to give it this much energy to get it up and over the hill. And then finally C. What is C? What do you notice about it? Good. The difference between the beginning and the ending. So the change between your final and your initial. So we're going to call that delta H. That's the energy that we're going to be referring to. And remember, whenever we have that delta in there, that's final minus initial. So in this case, we're thinking about products minus reactants. And that's going to be important that we do it in that direction, because we're going to see that here and just down at the bottom of our page, what that means. Which is next, actually. No, it's not. One more. Okay, so now what we're going to do is we're going to go through some numerical values on these. We've got a potential energy diagram drawn. And first one says, what is the potential energy of the reactants? So what's that number? Reactants. 20. And our units happen to be kilojoules per mole. I'm not going to write that from now on, but that's what our units are. Okay, potential energy of your product? 30. What about the activated complex? 50. The activation energy for the forward? Got to do some math here. 30. So the way that we got that was 50 minus 20. So this is where we started with our reactants. And here's our activated complex. What about your activation energy for your reverse? 20. So that one's going to be 50 minus 30. And then finally our delta H, 10. And again, it's pretty important to notice it's that 30 minus 20. So that 10 is a positive value. So we'll see that in just a second. Okay, so now we see why it's important to know the sign of our delta H, and it has to do with whether something is endo or exothermic. So our first example, again, we know that this is our reactants, these are our products. Oh, that's a P. Just looks like an R. There we go. So products minus reactants. In this first example, you have a big number minus a small number. What does that tell you about the sign of your delta H? It is positive, which means it is endothermic. In this situation, reactants and products. So products minus reactants gives you a negative value, which means it's exothermic. Maybe you just want to remind yourself that delta H is always going to be products minus reactants. All right, so now that we've got all that done, we can think about ways to lower the amount of energy that's required during a reaction. And what is this one going to be? Is this endo or exothermic? Exothermic, because you have a small number minus a bigger number gives you a negative value. Okay, so now we're going to look at a catalyst, and we talked about this yesterday. But what a catalyst does is it speeds up a reaction. So it speeds up reaction by lowering the activated complex, therefore requiring less activation energy. Okay, and it does this really just by providing an extra route. It's not that it makes that be the only pathway. It's just offering a separate pathway, one that's lower and doesn't require as much energy for it. So this is our example right here of our catalyzed reaction where we have this lower amount of activation energy that is required. We may as well, this is a good spot, let's go ahead and make a note here that we said this yesterday, a catalyst is not consumed in the reaction. And what we're going to see today when we work through some problems is that it's also not part of overall reaction. So now we want to think about how these reactions can all take place. We're going to try and relate it to collision theory, what we said. Oh, I'm sorry, I forgot about this slide. This is just reiterating what we said about an alternate route. So it doesn't lower the activation energy. A catalyst does not lower the activation energy of the original reaction. It just provides an alternate pathway. So I just learned that this is Thomas the train, and this is his friend, Henry the train, if I was told correctly. So Henry is taking an easier route with lower activation energy. He's going straight through instead of the higher route that Thomas the engine is taking. So it's just an example of the different routes. You've got both pathways. Oh, Thomas the tank engine. I was corrected. Not Thomas the train. It is the tank engine. Okay, yesterday we also talked about how preservatives are just a type of inhibitor. Again, that would be the opposite of a catalyst. And I'm not going to do that. You have enough examples. But here we go with looking at collision theory. And the question is, how can more than two molecules collide also with enough energy and the correct orientation all at once? And the answer is that's really hard for that to happen. So it's pretty difficult. What happens instead is that most reactions occur by a series of steps called reaction mechanisms. And for a reaction mechanism, this is what you should be writing down, your definition. Okay, so we just said that this is a sequence of reactions that produce an overall reaction. I also want to mention that these individual steps that you're going to see are called elementary steps. So let's also say a series of elementary steps. And what we'll be able to do is just add those up and get our overall reaction. So if we've got that, we can go to our first example. And here we see we've got three steps, three elementary steps that take place, and we want to be able to add those up and come up with an overall reaction, which means some things are going to cancel out. See anything that cancels out from one side to the other? N2O2, there's N2O2, there's N2O2, opposite sides. N2O, that goes away. That's pretty much it. What about H2? They add, they're on the same side. So when we add all of this together to get our overall reaction, we get 2NO plus 2H2 yields N2 plus 2H2O. And then the question is, what is our rate determining step? And every time that you're given one of these things, this is all experimentally determined, these values right here, how quickly something takes place. But all you're going to see is, yeah, this is pretty fast. This is pretty fast relative to the other steps. But this one is the slowest. You're always going to have one that's considered the slowest. It just means that your reaction is not going to take place any quicker than this one slow step. And that's kind of like the example of, waiting in line. Let's say that Mina and Reed are both in line and for lunch, and Mina Lee, she's got her money, exact change ready. She's ready to go. She knows exactly what she wants on her plate. But of course, Reed can't figure out, oh, should I have the chili cheese corn dog, or maybe I should have the Jell-O, or oh wait, where is my money? I can't find my money, and I can't remember my ID. So even though everybody else behind Reed might be ready and have their money ready, that line is not going to go any faster than Reed. So he is the slow step, the weakest link in this situation. He just wanted his name in this video, I think. So there, I put it in there. Okay, so our rate determining step would be our slow step. And I'm going to come back and say a little bit more about this slow step, but I guess one thing that we can add right now is that it determines two things. It determines the rate and the rate law, which means nothing to us right now. but when we come back and look at our notes later on, it'll be meaningful. So it determines the rate and the rate law. But another thing that we can look at right now is we can go through and determine what our intermediates are, as long as we know what the definition of an intermediate is. An intermediate is something that you create and then destroy. Therefore, it is not part, I cannot write, not part of your overall reaction. Okay, so if we look in our elementary steps there and we think about what we canceled out, we created N2O2. Oops. Then it became a reactant over here and we destroyed it. We created N2O, but then it became a reactant later on and we destroyed it. So both of those guys, N2O2 and N2O, are both going to be considered intermediates. Because they cancel out, they are not part of this overall reaction. Okay, so something else I wanted to mention about the rate law is that, again, this is determined experimentally. You guys would never have to come up with this information here that's determined for you. But when we come up with a rate law, and this is what we talk about tomorrow, I would write this down right here. That's just your generic formula for a rate law. Your rate is going to be equal to K, which is a rate constant, times the concentration of your reactants in your slow step. So maybe we just make a note that those are reactants in slow step. So now if we look back at our example, here is our slow step. If we want to write the rate law here, it's going to be rate equals K, that's my rate constant, times the concentration of my reactants in my slow step. The reactants are right there. So we're going to say N2O2 and H2, and we're going to raise each of those to the power of their coefficients, which we notice right here are just ones. Okay. Again, that doesn't make much sense to us today, but we're going to talk more about this tomorrow, and it'll make more sense then. Okay, just a little bit more here. We have one more example. And in this one, it says overall reaction again. So what do we see that cancels out? CO and O's and CLO. Okay, that looks like it. So if we add everything together, we get 2O3 goes to 3O2. So our intermediates, remember, let's remind ourselves, these we create, then destroy. But let's mention something again about our catalyst. I don't know that we wrote this down earlier. We know that they're not consumed, and what that means is that we start with and end with, but they're not part of overall reaction, just like the intermediates are not part of the overall reaction. But there's a little bit different wording here. Start with and end with them, create, then destroy. So if I wanted to look and see which one do I start with and end with? So yeah, start with it, end with it, but it's not part of the overall reaction. So that one is going to be a catalyst, your chlorine. Whereas you create, then destroy, CLO, and create, then destroy, oh. So both of those are going to be intermediates in that case. And then another thing that I think you guys have on your notes, but I did not put into my slide, it asks about rate determining step and the rate law. So on this one, our rate determining step, we know that step 1 is our rate determining step. So slow step is step 1. That's that. And if we wanted to write our rate law, you would say rate equals K times what? Your CL and your O3. And each of those, again, happen to be raised to the first power because of those coefficients that we see. Okay, and that's almost it. I'm going to add a little bit something else at the bottom here. Notice that this is just a repeat of what we've already said, but if you had this potential energy diagram, which one of those would be the slowest step, your rate determining step? I think it'd be 1 or 2. Step 1, because it's always going to be the one that has the highest activation energy is going to be your slowest step. And then another thing that you might come across is you have multiple peaks. So in this one example, how many elementary steps would you say you have? 3. How many activated complexes? 3. So you've got 3 activated complexes, 3 elementary steps. How many intermediates do you think you might have, possibly? You can create, then destroy, create, then destroy, created, then destroyed, created, then destroyed. And so it's really just 2 in this case, I thought, right? Minimum of 2 intermediates. So you create and then destroy. And then if we wanted to look at which one is going to be your rate determining step, which one do you think that would be? B. It'd be your second step. And the B's or the ABCs are really down in the troughs, but we've got 1 step, 2 steps, 3 steps. So I'd say your second step is your slow step. Okay, that is it for our reaction pathways and mechanisms.